Here is the first video on a series of few videos that are going to show how to solve systems of differential equations. And let's start first with how matrices even are used. So let's take a look at a system of equations. Suppose I have 3x minus y equals 4, 2x plus 5y equals 9. Now we can represent that this system as an augmented matrix. So I can rewrite this in the form where I just list the coefficients and then the answer column. So this is one way to represent this series, or if you want, this system of equations. A second way we could represent it looks like the following. I could do 3, 2, negative 1, 5. Finish off that matrix. And then I can have a vector xy, and that could equal the solution vector for 9. This way is most like the way we'll work with problems in this course. Many times you'll simply see something like this. You might represent this as ax equals f, something like that, where in this case this guy right here is the a, x with the arrow over it is this column vector, and then f with the arrow over it is the solution column or solution vector. Now in these representations, I'm using x with an arrow over it to represent a vector. Your textbook use bold letters for vectors. So I'm not exactly sure how I'd represent it. So for example, instead of this, your textbook, let me see if I can make myself a really thick line. Yeah, let's do this. Your textbook might instead represent it as something like this. So I'll put it back. Just so you know, in textbooks they'll use bold lettering. Everybody else, because it's impossible. I can't pause and do this every single time I want a vector. So I'll put an arrow over top of the vector to represent it. So anyways, this type of an equation is the kind we're going to be looking at in solving solutions or systems of differential equations. So to start off, as my first example, write the system in matrix form. So the system that we're given looks like dx over dt equals 4x minus 7y. On the other hand, then, we have dy over dt equals 5x. So as a matrix form, the first thing I might think of doing is writing this column as, say, maybe dx over dt, dy over dt, and that would equal, I'll copy the coefficients, 4 is in front of x there, Negative 7 is in front of y. And we've got a 5. There's a 0 in front of the y in the second equation. And then I'll put my x, y over here. More likely than not, you'll see it something like this. This vector will be represented by x with an arrow over it, but prime, indicating it's a derivative, a vector of derivatives. And we'll still list the matrix, but then we'll just put an x bar over here. So our game plan typically will find to find the value of x bar or xy. Same problem, different things, matrix. Write this system in matrix form. So here I have dx over dt equals x minus y, dy over dt equals x plus 2z, and dz over dt equals negative x plus z. So we could write this simply as x arrow prime equals, my matrix now, it has an x, y, and z, so it's going to have 3 rows and 3 columns. For instance, there's a 1 in front of the x and a negative 1 in front of the y. But there's a 0 in front of the z. Then here I have 1 in front of the x, 0 in front of the y, and 2 in front of the z. And then finally I have negative 1, 0, 1. And we'll just put x, the vector x will represent x, y, z. Same deal. Here we'll have dx over dt. This time will equal 3x plus 4y plus e to the negative t times sine of 2t. dy over dt equals 5x plus 9z plus 4e to the negative t cosine 2t. And then finally dz over dt equals y plus 6z minus e to the negative t. So now you have extra stuff here that's not attached to x, y, or z. These kind of things will represent, I wouldn't call them particular solutions, but they are preventing each of these equations from being homogeneous. So you might call this a non-homogeneous system. Well then, to write this, I can still do my x arrow prime, copy my matrix. So I have 3x, 4y, 0z. So I'll put a 3, 4, 0. Then I have 5x, 0y, 9z. 5, 0, 9. And then I have 0x, 1y, 6z. So 0, 1, and 6. And then for convenience, I'll use x arrow. But then you have additionally this vector here, which prevents it from being a homogeneous system of equations. So we'll see e to the negative t sine of 2t. I'm going to have to move over a little bit. And then I have 4 e to the negative t cosine of 2t. And then finally I'll have negative e to the negative t. Now, for convenience, they'll most likely do something like this instead. I'll put my matrix as usual. But then if you notice, there's an e to the negative t attached to everything here. So the second vector I can write as sine of 2t cosine of 2t negative 1, and have that all times e to the negative t. In fact, this is what we call scalar multiplication. If I multiply just a single number, which for any t, this is a single number, and I put it out in front or behind a matrix, that means I'm going to multiply to each of the three items or members of this vector. This time let's reverse this. Let's write without matrices. So I'd like to write it as a system of equations. And the look of it is this. X arrow prime equals, let's see, we have 7, 5, negative 9, 4, 1, 1, 0, negative 2, 3 times x arrow plus 0, 2, 1 times e to the 5t minus 803 times e to the negative 2t. And so on the left, I automatically have dx over dt, dy over dt, dz over dt. So let me go ahead and plug this stuff in. Here's what it looks like then. I'm going to have dx over dt, and you can read along the first row of this matrix and get 7x plus 5z, 5y minus 9z, and I've got this other stuff, plus 0 e to the 5t minus 8 e to the negative 2t. Then moving across the next row, we have dy over dt. That'll equal 4x plus 1y plus 1z. And then I have plus 2e to the 5t. And then I have minus 0e to the negative 2t. Of course, it's not necessary to write these things with 0. dz over dt, I'll have 0x minus 2y plus 3z, so I have minus 2y plus 3z, and then I have plus e to the 5t minus 3e to the negative 2t. And as I mentioned, nobody would write the things that have a 0 in them. So just erase them or don't even write them to begin with. And there's your system of equations. Another one, write without matrices. Here what I give you is d over dt xy. When I write that, that means that you'll apply the derivative to both x and y. X and y, I didn't say it, but they are functions of t, each one of them. And this is supposed to equal 3, negative 7, 1, 1, xy, vector xy, plus 4, 8, sine of t, plus then we have t minus 4, 2t plus 1, e to the 4t. So to rewrite this as a system of equations, do the same thing. Just go row by row. Starting with the first row, I'll get dx over dt. That'll equal 3x minus 7y plus 4 sine of t plus t minus 4 e to the 4t. and then dy over dt. Read the second row. Yeah, I get x plus y plus 8 sine of t plus 2t plus 1 e to the 4t. I'm going to try to make my t's not look like plus signs, so I try to give them some curve so they're easily distinguishable. Now let's take a look at some equations and verifying solutions. So verify that x arrow, which equals 5 cosine of t, 3 cosine of t minus sine of t, all of that stuff, times e to the t, is a solution to dx over dt equals negative 2x plus 5y, dy over dt equals negative 2x plus 4y. Now what we have to do is make sure that this vector works in both the equations. So here's what we have. The x that I'm proposing from this vector, the function x, will be 5 cosine of t times e to the t. And then the y portion will equal 3 cosine of t minus sine of t times e to the t. So I have 3 cosine of t minus sine of t times e to the t. And let's see how it works out here. I'll start with taking the derivative and verifying this first equation. So let's start with dx over dt is supposed to equal negative 2x plus 5y. So first, let's take the derivative with respect to t of x. So I'll have to use the product rule. When I take the derivative of cosine, I'll get negative sine, so I get negative 5 sine of t times e to the t, and then the second part is the derivative of e to the t, and that's nothing. So I get 5, well, it isn't nothing, it's just itself. And then on the other side, I'm supposed to have negative 2 times x. X is 5 cosine of t times e to the t, and then plus 5y. And let's see if it all jives. Here, there's not much I can really do on this side, except I could factor out an e to the t and even a 5. So if I take out a 5e to the t, that'll leave me with negative sine of t plus cosine of t. And we'll try to do the same thing here. I notice that there is an e to the t attached to everything, so I'll pull it out. And what is left? Here I have negative 10 cosine of t. And then I have plus 15 cosine of t. And minus 5 sine of t. And let's see what all happened here then. The left side is about as simplified as it's going to get. The negative 10 and the positive 15 simplify, so I'll have e to the t times 5 cosine of t minus 5 sine of t. It's at this stage which I think I've got it. Obviously, if I factor out a 5, I'm going to get exactly what I have on the left-hand side. So I verified one. Now let's work the second one. Here we have dy over dt is supposed to equal negative 2x plus 4y. So let me get my derivative for y. Same thing, it's a product rule as before. I'll take the derivative of this stuff in parentheses first, negative 3 sine minus cosine of t times e to the t plus, and then we'll just take the derivative of e to the t, which will do nothing, and I'll leave the first part alone. 3 cosine of t minus sine of t times e to the t. On the other side, I'm supposed to have negative 2 times x. Where did x go? X was 5 cosine of t e to the t. Plus 4y. Y is, oh, there it is, 3 cosine of t minus sine of t times e to the t. And let's simplify each side. I'll pull an e to the t out of the left. What would have been left? What's remaining here? A negative 3 sine of t and a negative sine of t. That'll give me a negative 4 sine of t. And then I have a negative cosine and a 3 cosine here, so I get plus 2 cosine of t. I'll do the same game on the other side. I'll pull out an e to the t from everything, and let's see what's left. Negative 10 cosine of t plus 12 cosine of t minus 4 sine of t. And let's see if it jives with my left side. I get positive 2 cosine of t. There it is. Negative 4 sine of t. Gotcha. Verify that x arrow equals 1, 3 e to the t plus 4, negative 4 t e to the t is a solution to x arrow prime equals 2, 1, negative 1, 0 x with an arrow. Let's take a look. When I look at this x, the way you would write it as a single vector like here, to write it as a single vector here, I can add these all together, and from here you can get x with an arrow over it equals, I can write it as one vector where my first row will be 1 times e to the t plus 4t e to the t. And then for the second row, I'll get 3e to the t minus 4t e to the t. The left side I can represent as dx over dt, dy over dt. This is a system of equations. On the right hand side, I'll get 2x plus y. And on the right side down here, I'll get negative x. And then let's see what happens here. My x portion, we're going to try my x that I'll use will be e to the t plus 4t e to the t. And I want to make sure that works in both of the equations as well, and plug in the y also. So let's go ahead and start with the derivative of that. So I'm doing dx over dt. That's supposed to equal 2x plus y. So dx over dt, that'll be e to the t. I'll have to use the product rule for this part, plus 4e to the t, and then finally plus 4t e to the t. On the right side, let's go ahead and plug in my x. I have 2 times e to the t plus 4t e to the t. This first row is x, the second row is y, plus 3e to the t minus 4te to the t. Now let's simplify both sides and just make sure they're equal. So I'll get e, here it looks like a 5e to the t, 5e to the t, plus 4te to the t. That equals, let's see what all we have over here. I have 2e to the t plus 8te to the t plus 3e to the t minus 4te to the t. And let's take a look. If I look at, I have 5e to the t, I have 2e to the t plus 3 to the t, there's 5e to the t. 4te to the t, I have an 8te to the t minus a 4te to the t. So this all works out. On the other hand, let me check out to see if the derivative of y equals the negative of x. So going back, y is equal to 3e to the t minus 4te to the t. And I need to also verify the equation dy over dt simply equals negative x. So let me plug those things in. I'll have the derivative of this is 3e to the t, product rule again, minus 4e to the t minus 4te to the t. And then my x, there it is right there, I'll put negative e to the t plus 4te to the t. And let's see what happens. I'll just simplify the left-hand side a little bit. I have negative e to the t minus 4te to the t. And the right side, I can see right now that they're equal. Well, it's assumed that you've seen matrices sometime in your life. It may have been a while before you've seen how to actually multiply and do that kind of stuff with them. So let's look at some of the common things that you'll be doing with matrices. And one of them is taking a matrix and multiplying it to a column vector. The rule for this is as follows. You take this row and you match it with the column vector. That means I take a times x plus, and then you do b times y. For the next row of this vector, I go to the next row in the matrix. Now I do cx plus dy. If I want to do bigger matrices, if I say I do a 3 by 3 matrix, it's usually more useful if I resort to the common subscripts, because trying to use up all 9 letters, you're going well into the alphabet, and then you'll be using things like I and some other letters that I'd rather not use. So let me use this common notation to represent a 3 by 3 matrix. And the way it works is the first number gives you the row and the second number gives you the column. So if you look at A12, the first row, second column, down here, third row, first column. That's how they work. Now if I'm to multiply that to x, y, z, you follow exactly the same thing I did for 2 by 2 matrices. This here's a 3 by 3, this is a 2 by 2. And I will get a vector, but it'll have 3 rows. I take this first row and I multiply it to this column. It means I take a11 times x plus a12 times y plus a13 times z. And then I go to the next row and do the same thing over again. So a21 times x, a22 times y, and a23 times z. And finally, the third row matches with that column as well. a31x plus a32y plus a33z. And it's important to note that this vector, since I'm adding these things together, only has 1 column, and it has 3 rows. Notice the order of the coefficients follows this matrix exactly. In fact, many times, this matrix is called a coefficient matrix. Other things that you can do, if I have a number times a matrix, you just multiply each entry by that number. Let's see what else is there. If I add two vectors, you add component by component, so you just add across x1 plus x2, y1 plus y2. There are Wronskians. And they're used to determine linear independence, just like before. You may know it in your typical linear algebra class as simply the determinant. But anyways, let's suppose that x1 arrow equals 1 negative 1 e to the t, x2 equals 2 6 times e to the t plus 8 negative 8 t e to the t. And you should recognize this. Some sort of a solution has been repeated when this kind of thing happens. So anyway, suppose these two vectors are solutions to a system of differential equations. Do they form a fundamental set of solutions? So I don't know what the system of equations was, but the way we tested for fundamentalness is to show that the Wronskian does not equal 0. So let me go ahead and put these in here. So we're going to look at the Wronskian of x1 arrow, x2 arrow, and it's just a 2 by 2. Since you have 2 rows, you also have 2 columns. Let me get my first column here. I'll have e to the t, then I'll have negative e to the t. Notice I'm not doing anything with derivatives. This is just a straight up determinant. I'm not sure Wronskian is the best word for it. This is just the determinant. If the determinant is non-zero, the system of equations is linearly independent. Here we'll have 2e to the t plus 8t e to the t. And then we have 6 e to the t minus 8t e to the t. And as you'll recall, the way we compute this thing is we multiply across this diagonal here. So top left to bottom right. That equals e to the t times 6e to the t minus 8t e to the t. And then I subtract multiplying the other diagonal. So that will become plus e to the t times 2e to the t plus 8t e to the t. Now, let's see what happens here. Here I'll get, I'll just multiply through. I'll get 6e to the 2t. Then I'll get minus 8t e to the 2t plus 2e to the 2t plus 8t e to the 2t. Now, I was hoping that the 8t's would cancel out, because if they didn't, it would have an opportunity to be 0 when t equals 0. And together then, I get 8e to the 2t, and there is no way that equals 0. So this solution, this is good on negative infinity to infinity, since the Wronskian is definitely not going to be 0. Let's try another one. Now you can see these look very much like they might be a particular solution and then two solutions of the complementary function. So with that in mind, it doesn't really matter if I have that in mind or not. Let's see if that forms a fundamental set. So suppose x1, x2, x3 are solutions to a system of differential equations. Are they a fundamental set? So same deal. I'm going to take the Wronskian x1, x2, x3 and take the determinant of the following matrix. Here I'll have 1, 6, negative 13. The first column is really nice. Second column is not as nice because I got this e to the negative 4t attached. So I have e to the negative 4t minus 2 e to the negative 4t minus 1 minus e to the negative 4t. And then for the last column, I'll have 2 e to the 3t plus 3 e to the 3t, and finally negative 2 e to the 3t. Then the way you do the determinant of larger matrices is done by choosing a column or a row to expand across, they call it. So let me just show you. If I pick the first column, here's how it works. I take this number 1 and kind of like, let me put a line across and then a line going this way. If I do that and cross out the row it's in and the column it's in, what's left is a matrix, and I'm going to take the determinant of it. Negative 2e to the negative 4t, 3e to the 3t, negative e to the negative 4t, negative 2e to the 3t. Okay, so that's for the 1. Now I go on to 6. I change sign. That's the way you do it. I go positive, then negative, then positive. If it was a 4 by 4, then I would have negative again. The way you do this, you don't want to go like diagonal or anything like that. You either want to go across or down a column or across a row, and do not vary. Stick with that row or column. Usually it's helpful if you have 0 entries, and then you might choose a convenient row or column based on the number of 0 entries. But now what I'm going to do, let me see if I can get these lines to disappear, which I did. Now I'm going to cross out the row that 6 is in and the column that it's in, and the stuff that's left over will form a 2 by 2 matrix. So I have an e to the negative 4t, 2e to the 3t, and then I have negative e to the negative 4t, and I have negative 2 e to the 3t, and then finally I'm plus again, so negative 13 makes it a minus. Let me see if I can get rid of these lines, and the same thing goes with 13. Get rid of its column and its row, and what's left is the matrix that I'm going to take the determinant of. So I have e to the negative 4t, 2e to the 3t, negative 2e to the negative 4t, and then finally 3e to the 3t. And let's see what we get for each of these things. And of course the 2 by 2 matrices, you go diagonal and then you subtract the other diagonal. So when I go down this diagonal, I'll get 4e to the negative t. And then when I go up this diagonal, the negative will cancel, and I'll get plus e to the negative t. And I have minus 6 times, if I go down this way, I'll get negative 2 e to the negative t. Then if I go this direction, I'll get positive 2e to the negative t. And then finally, I'll have negative 13 times Going this way, I'll get 3e to the negative t. And then going this way, I'll get plus 4e to the negative t. And then let's go ahead and add everything up. Here I'll get 5e to the negative t. Here I'll get negative 6 times 0. That was a nice one. And then finally minus 13 times 7e to the negative t. I think I made a mistake right here. Going down, that's a 4. Going back up, I missed this 3 here. There's a 3 right there. That changes this. Let me fix it up a little bit in here. This here is plus 3e to the negative t. That means this 5 is not a 5, but it's actually a 7. And then I'll have 7e to the negative t plus minus 91e to the negative t. I have negative 84e to the negative t. And that, of course, does not equal 0. So this is also good on negative infinity to infinity. For the next example, let's verify that x arrow sub p equals 1, 3 is a particular solution to x arrow prime equals 2, 1, 1, negative 1, x arrow plus negative 5, 2. Well, these are just numbers here. Their derivatives are very simple. That'll be 0, 0. The derivative of 1 is 0. The derivative of 3 is 0. So that's an easy one. I'll get 0, 0. And now I want to plug it into that. So I have 2, 1, 1, negative 1 times 1, 3 plus negative 5, 2. So everything's going to happen on the right, and I better come up with 0, 0. So I'll do my typical multiplication. Remember, this is going to be 2 rows but 1 column. So I have 2 times 1 plus 1 times 3. And I'll have 1 times 1 minus 1 times 3 plus negative 5, 2. Then I'll have 5. Looks down here, I'll have negative 2 plus negative 5, 2. And then when you add component-wise, 5 plus negative 5 will give me the 0, and negative 2 plus 2 will give me the 0. Let me verify that. Let's have another particular solution. X sub p arrow. This time a little one with a little more complication. We have sine of 3t, 0, and then cosine of 3t. Verify that is a particular solution to, I'll have x arrow prime equals 1, 2, 3, negative 4, 2, 0, negative 6, 1, 0, x arrow plus negative 1, 4, 3. So let's go ahead and throw it in and see what happens. First, on the left-hand side, I have the derivative vector. So let's take the derivative of this vector, and I will get 3 cosine of 3t. The derivative of 0, of course, is 0. Then I'll have negative 3 sine of 3t. On the right, then, I have my 1, 2, 3, negative 4, 2, 0, negative 6, 1, 0, and I'm multiplying it by sine of 3t, 0 cosine of 3t, and then don't forget to add this vector when all that's done, negative 1, 4, 3. And let's see what happens. I need the right-hand side to match this left-hand side. So remember, this matrix now, we'll have a vector that has 3 rows but 1 column. So let's go ahead and start that. So what you do is 1 times sine of 3t plus 2 times 0 plus 3 times cosine of 3t then I'll have, before I go on, I made a boo-boo, as I usually do. This is supposed to have after it a sine of 3t, so let me attach that. I noticed it because just having numbers would not have been compatible with what I have so far. Now moving to the next row here, I'll have negative 4 times sine of 3t plus 2 times 0 again, plus 0 times cosine of 3t. And then I'll move on to the last row, negative 6 sine of 3t, 1 times 0, plus 0 times cosine of 3t. While I'm at it, I'm going to make this into a single vector. I'll pull this in. I'll have negative sine of 3t. Then I'll have 4 sine of 3t. And finally I'll have 3 sine of 3t. And let's go ahead and add everything up and see what happens. Here I have 1 sine, 3 cosine, but then the negative sign will cancel the sign out. So I'll be left with 3 cosine of 3t. For the second one here, I have negative 4 sine of 3t and nothing else, but then I have plus 4 sine of 3t, and that'll give me a 0 there. And then finally I have negative 6 sine of 3t plus 3 sine of 3t will give me negative 3 sine of 3t.